Have you ever stopped to think about how a machine, just a chunk of silicon and metal, actually understands what we tell it to do? Today, we're going to pull back the curtain on the computer's secret language. Let's get into it.
So let's start with something really simple, something you could solve in a split second. C equals A plus B. For us, that's nothing. But for a computer, that single line of code is the start of an incredible journey, from a language it can't understand to the raw electricity it was built for. So how does it actually make that leap?
Well, here's the fundamental problem, right? We talk to computers using high-level languages, like Python or Java, that are abstract and, make sense to us humans. But the processor, the actual brain of the machine, it only understands the physical language of electricity, ons and offs, ones and zeros. There's this huge disconnect between our world and its world.
And this disconnect, it actually has a name, the semantic gap. Semantic just means related to meaning, so this is literally a meaning gap. It's the vast difference between the meaning of our command, hey, add these two numbers, and the dozens, maybe even hundreds of tiny little hardware steps the machine has to take to actually do it. Bridging this gap is pretty much the core challenge of all computer design.
So how on earth do you solve that? How do you get the software and the hardware to finally talk to each other? Well, you need a carefully crafted set of rules that both sides can agree on. You need an official translator, a common language that can sit right there in the middle. And that translator is the Instruction Set Architecture, or ISA for short. Just think of it as the official vocabulary of a processor. It's the complete list of all the basic commands the hardware knows how to do, things like add, load data, or store data. It is the absolute, fundamental contract between the physical world of the chip and the abstract world of code. A great way to think about this is like an architect's blueprint for a house. The software programmer is like the client, saying, I want a kitchen over here. The hardware engineer is the contractor who has to physically build it. The blueprint, that's the ISA, is the common language they both understand. It makes sure that what gets built is exactly what was intended. Okay, so we know we need this blueprint. But, and here's where it gets really interesting, it turns out there's not just one way to draw it. Over the years, two major competing design philosophies have emerged, and they have very different ideas about the best way to bridge that semantic gap. On one side, you have CISC, which stands for Complex Instruction Set Computer. The name kind of gives it away, right? The philosophy here is to make the hardware really powerful. You give it one complex command, and that one command can trigger a whole cascade of actions inside the chip. Then on the other side, you've got RISC, Reduced Instruction Set Computer. This philosophy is the total opposite. It's all about simplicity. You have a small set of very basic, very fast instructions, and you rely on clever software to string them together to get the job done. So that's the theory. But how does this philosophical difference actually play out? Let's go back to our simple example, C equals A plus B, and see how these different blueprints would tell the computer to actually do it. This table just lays it out so clearly. Look at a stack-based ISA, which kind of uses a last-in, first-out pile. It needs 4 separate steps. A register-register architecture, which is pretty common in RISC designs, also needs 4 steps, but it's doing something different, loading data into these little temporary holding spots called registers, adding them, and then storing the result. The big takeaway here is that the design of the ISA directly changes the number and the type of instructions you need for even the simplest task. But here's the thing. It doesn't really matter if the instruction is simple or complex, whether it's CISC or RISC. Once an instruction arrives at the processor's doorstep, it goes through the exact same fundamental life cycle. It's this simple, steady rhythm that beats at the very heart of all computing. And that rhythm is the fetch, decode, execute cycle. Super simple. First, the processor fetches the next instruction from memory. Second, it decodes it. It looks at the instructions code and figures out what it's being asked to do, like add or load. And finally, it executes the command, sending the right electrical signals to make it happen. Fetch, decode, execute, over and over and over, billions of times a second. It's kind of mind-blowing. Now, I know this might all seem like some super low-level, geeky engineering debate, but trust me, these design decisions that were made decades ago have a massive and direct impact on the technology we all use every single day. This is where it all hits home. This simple, power-sipping nature of RISC designs, that's exactly why ARM processors are in almost every smartphone, giving us that all-day battery life we crave. Meanwhile, the powerful, complex instructions you find in CISC designs, like the x86 architecture in most PCs, have traditionally given us that raw performance for heavy-duty work. It's all a trade-off, right? A balance between performance, power, and cost. And this whole debate, It is far from over. In fact, it's heating up like never before, all thanks to a revolutionary new blueprint that is seriously shaking up the status quo. And its name is Risk-V. So what makes Risk-V such a big deal? Well, it takes all those great principles from Risk, simple, efficient, modular, and it adds one huge, game-changing ingredient. It's open source. For decades, ISAs have been proprietary secrets. You had to pay massive licensing fees to companies like Intel or ARM just to use their blueprints. Risk-V is totally free for anyone to use and modify. This just completely democratizes chip design. And this really brings us to a fascinating final thought. For decades, only a handful of giant corporations could design a processor. Now, with an open blueprint like Risk-V, anyone can. A startup, a university, even a hobbyist in their garage. So the question isn't just CISC versus RISC anymore. It's about what happens when the ability to design a computer's brain is open to everyone. What new ideas, what new efficiencies, and what new forms of computation will that unlock for all of us?